Hey guys, so welcome back to your next class of Catalyst Concepts. In the previous class, we were looking at what exactly is the drift velocity of an electron. Basically, with what speed or what average speed an electron will move through a conductor when it's put inside a closed circuit, right? Okay. Today, we are going to discuss that a little to go a little more ahead, right? One question that I have is, if an electron is moving, right, in a certain direction with a certain amount of energy, does that not mean that there is something that's actually giving the electron the energy to move, right? Because if you leave an electron be, it will just keep moving randomly. That's what we had studied. But for an electron in a circuit to be moving in an ordered manner in a certain loop, for all of them to go in one way, there has to be some sort of energy being given, right? Some sort of force being put, right? Uh, so if you think along these lines, I think we can talk about one thing that we had studied previously in our grade 9. Okay, that one thing being called as let's say work. Okay, so today we are going to look at what form of work happens in an electric circuit. Okay, so let's imagine our general simple electric circuit like this. Okay, so let's just like maybe keep a bulb or whatever it is, right, and the battery. Right, now I'm going to take one small section of this circuit over here, right? I'm going to draw that brick. Basically, I'm taking a cross section of this, right? So this is our conductor. Okay. Now, this end is connected to positive terminal. This end is connected to the negative terminal, right? Okay. Now, I know that this will have a certain amount of length, right? This section of the conductor. Let's just say there's some length. Okay. All right. Now, the electric field is generated whenever a battery is connected to a conductor. That's something we study. So this means there is some field running through this, right? So since it runs from positive to negative in this direction, it means over here the electric field is going like this, right? Through it like this. Meaning we are talking about the electric field in this direction, right? Now, all right, if the electric field is going in this direction, we know that the electrons are actually moving in the opposite direction, which is this direction, right? Because they always move in the opposite direction of the electric field. Okay. Since the electrons have to move against the field, there is some sort of work being done, some sort of force being given, what we call as electric force. Okay, there's some electric force that is being given to the electrons to move against the field. All right, we're going to try to find out how much work exactly happens. So if you remember the definition of work, we had it like this: work equals to, I'm sorry, work equals to force into displacement, right? Ninth class. Now, first let's look at what exactly is this displacement. How much movement are we looking at? Okay, where since we're taking one small section of the conductor, we'll say that we're looking at this section of the conductor. Okay, this is our nothing but our displacement. Okay, so I can now write the work done on these charges, right? Remember, these are the charges that are moving. Okay, if it's charges moving, it means the force is being exerted on the charges. All right, and we know that charge generally means q for us. Okay, I'm just going to put that down over here. Okay, so we're looking at the work being done on q amount of charge in a conductor whose size is L. All right. Now I can write work equals to F into L, which is nothing but the length of this conductor. All right. Now let's look at what exactly is this force. All right. Let's say F is a force that is generated by the electric field called the electric force, right? So I will say that F is nothing but electric force on Q amount of charge, okay, on all the free charges that are called Q charges, okay. I'm going to call this as F with a small e, okay. Now, if that is what I will call it, then I will write this as W equals to F small e into L. Okay. So the work done by this electric field or this electric force is nothing but the force it generates on the charges multiplied by the displacement it's creating in the charges, which is along the length of the conductor. Right? Simple enough. Okay, so we have figured out what is the total work on Q charges. But what I want to find out instead is what is the work done on a single charge, on a unit charge. Okay, work done on unit charge, or let's say per unit charge. Per is a simpler word that will tell you exactly what operation you need to do. Okay, if the total free charge is Q and this is the total work, then I will say work done per unit charge is nothing but work done per the total charges, right? Whatever the charges are. If you divide these two, you'll get work done per unit charge. All right. So if I do this, I already know what is the value of for work, which is nothing but electric force into length of the conductor divided by Q, right? So if I have this formula, work equals to FEL, electric force into length divided by Q, I can find the work done per unit charge. But there is a certain name for it. Okay, there is a certain name for this work done per unit charge. We call this as potential difference. Okay, this is called as potential difference. Okay, potential difference is nothing but how much work is done on a single charge when it is put in a circuit. Okay, when you put in a circuit, how much work is done on a single charge to make it move through a certain amount of distance. Okay, the single charge part is important over there. All right, so this is potential difference, and the symbol for potential difference is nothing but V. Okay, so V equals to nothing but work done per unit charge is nothing but Fe into L divided by Q. Now, since it's a measurable value, it should have some units, right? Something we've learned already. Everything has a certain type of unit. Okay, so if we have units, what exactly is the unit? We know that if V equals to V equals to, let's say, W by Q, right? We know work has certain units, and that is nothing but joules. Okay, the unit of work is joules. Okay, the unit of charge is nothing but coulomb, that we saw in this chapter only previously, right? So I can say the unit for my voltage is nothing but joule per coulomb. Okay, joules per coulomb. Okay, this joules per coulomb is also called as volt. Okay, volt. All right, volt or volts. Okay, so voltage, since this is going to be confusing with the alphabet V, I'll just write this as the word voltage or potential difference. Potential difference equals to W by Q, which is nothing but J divided by C, joules per coulomb, which is nothing but volt. So potential difference is calculated in the unit volts. Okay, the symbol for potential difference is also V, and the symbol for a unit is also V. Okay, kind of very easy way to figure out that potential difference unit is volt. Okay. So what exactly is 1 volt? How do we define 1 volt? Okay, we say 1 volt is the potential, or we can say 1 volt potential difference is created when 1 joule of work is done to move 1 coulomb of charge through a circuit. Okay, when 1 joule of work is done to move a coulomb of charge. All right, charge, not current. Okay, 1 joule of work done to move 1 coulomb of charge. Then we say that the potential difference is 1 volt. All right, so just remember this, what is the unit for potential difference, how to calculate it, and how we define it, right? And this is also something that you can keep in mind, not that essential, but yeah, let's see if we might come across numerical. So when we do, we'll have to use the formula if you. Okay, so that's it for today. In the next class, when we come back, we'll go through the next topic and we'll just go ahead and see what there is. If you have any questions, doubts, please drop them in the comment section below, and I'll see you again in the next class. Thank you very much.